Welcome back. Our final panel today is panel 4, reasoning enhanced neural networks in wireless signal processing. So this panel is related to wireless signal sensing. So now the current president of IHB Signal Processing Society, Costa, has kindly agreed to chair this panel. So Costa, please.
Thank you, Chairman. So we have, as you see, 3 questions. It's a little bit more structured or different from the previous, ones. So the first question that we'd like to use to open the panel this afternoon is why we need, smarter wireless signal processing. Remember, the operand word there is smarter. So we assume that we are smart, and we want to become, smarter. And we have identified some, pointers that perhaps can help you to answer this question or contribute to the discussion. So traditional neural networks, the kind of neural networks that we discussed in the morning, the deep neural networks, the transformers of the universe, and so on and so forth, they are good in certain tasks of interest to us, but may fail across different conditions, the changing conditions, and we touch upon the interpretability and explainability of the so-called black box. So with that in mind, the question is, what else needs to be done, if any, right, to make us look, smarter and better?
I guess this is the answer is very obvious, right? Anyway, so I think when we start talking about SIG-G, I think there is no question AI is going to play a very important role. And in this context, I think signal processing is very, very critically is one of the, I guess I'm trying to think because my brain is dead. I don't know how. You should not have picked up on me. But seriously, I think the signal processing obviously a very important component of AI and machine learning, and I truly believe that AI is going to be an integral component of SIG-G moving forward to that. And as I mentioned this morning, a lot of the I think the system are becoming so complicated. And I mentioned, for example, and I'm not sure that traditional analytical methods will be able to manage all of that. And in that context, I think the use of AI and machine learning is going to be critical in order to allow a lot of the stuff, the optimization and so on that we would like to do. So in that case, I think that's the reason why we need a smart wireless signal processing. I hope that was really
great.
Coherent.
So, Costas, I would like to sort of direct this question to more outside the communication problem, because now the opportunity is if we have a sensing data, then there's a lot of things, and large amount of things were related to signal processing, that you start from the point cloud to, for example, to reconstruct the object. This is a very interesting signal processing problem, as especially with the neural network as a tool, and to do even detailed restoration or even rendering potentially on material and all this. So those are the big area. We don't know yet how far the signal processing can advance to extract the simple the sensing data. Basically is the direction and the depth.
So,
please, no, please follow up.
Because I felt I was still sleeping, but let me. So I think one of the things we did, especially with respect to the traditional neural networks, one of the we've done quite a bit of studies on that, and what we have found is that the traditional neural networks, they are not actually very good in the sense of what you've asked the question about generalization across different conditions. What we have found, for example, if the network is not too large, for example, the number of users and so on is not too large, it actually worked pretty well. However, when you try to scale the network, what we have found is that the accuracy and so on becomes extremely bad. On the other hand, we have tried to use things like the graph neural networks, and what we have found is that the system can work way, way better, particularly with respect to generalization, with respect to scalability. So that's something I just wanted to add. Thank you.
Yeah, I wanted to add, I think an area that could be just about to explode, but let me preface it as a realist, skeptic scientist, if you will. The wall between the physical layer and the app has helped a lot. So that's kept the pipe, as a conduit, and then the application guys can do all sorts of fancy, creative things, and they don't talk to each other. And that world has been very generous, provide a lot of useful applications. But if we were able to break that wall and start do joint source and channel coding, or in these days we call it semantic communication, maybe more general term, it's very wide open. So if I'm taking a picture of a sign in Chinese and I want it in Spanish, then the tremendous amount of compression that can happen if the compression engine were to be aware that all I care is the translation. I don't care about the font. I don't care about the detail of whatever graffiti is around the sign, or et cetera, et cetera. I'm not talking about photographic quality resolution. Just want the meaning of the words. And so can you imagine the level of compression there? It can be phenomenal. At the same time, imagine the cognitive challenge of whatever agent is trying to figure out that all that is that the user is requesting is a translation. Maybe I did press the button that says translate, and then if that information could be pushed down or up, whatever it is, down to the image compression engine that is about to create a packet to send up to the AI that's doing the translation. That's just one example. There are many, many others like that. But with word of caution, I learned this at a semantic communication workshop, and there was a very interesting compression where you could compress license plates. So the reconstruction after tremendous orders of magnitude compression over classical solutions was amazing, because every character looked like a real character of language, Western language, Latin-based language. And then, but every now and then it would make a mistake and it would change a F into an L or an F into a T or something like that. And then I said, wait a second, this is extremely dangerous. If I'm just trying to translate a sign to get to the tourist spot, that's fine. But if it's looking at my license plate and I'm getting a ticket because it made a mistake and that plate became my plate just because of a confusion, then who's going to pay that ticket? And so there is a whole trail of traceability, liability, auditing, which, this whole space is wide open. We haven't even begun to explore the possibilities. Performance can be hugely advantageous, but we are opening up a whole number of other problems, whether they're signal processing or a combination of app development and security and identity and privacy, etc. But I think the future, in terms of interesting problems, is just in front of us, amazing.
Yeah, I think my answer is a combination of what Ben said and what Ronaldo said. If you look at the signal processing, the main operation on the signal processing, wireless signal processing, is detection and estimation. I mean, that's all it is. So how can neural networks help with this? So far, traditionally, we've been using explicit unique words or pilot to assist with estimation and detection, and or is a data-based detection that we use for all of this. But all of these are fixed, like unique work is fixed for all the environment, right? So what the neural network could help is with sensing. Sensing effectively gives an eye to the network that we haven't had. It can see the environment. It says it's urban environment, it's built-up environment. Therefore, I need to set the taps of my equalizers according to that channel, rather than being explicitly sending a message or unique word in order, and then equalizer try to work very hard to find the equivalent, the channel that the system is operating. So from that point of view, as well as from channel coding point of view, is with the intelligence in the neural network it can effectively, like semantic communication, you don't need to explicitly add redundancy because of the channel. So then it says by the meaning of the content and etc., rather than just digitizing everything and sending it, then it can reconstruct the picture or image or even the video. It can do. So from that point of view, it has the potential to save and help with the traditional way of signal processing, that we digitize everything and we transmit it and protect it and we try to estimate what was transmitted at the receiver side.
Yeah. Perhaps I should have said that, that this is also in the context of the discussion that we had in the morning about, the integrated sensing and communication, right? You have new sensors that provide the additional pieces of information that are readily available, to you. And then based on, this, you can have the new applications, right? On top of the classical applications that you have. So the question, therefore, is what, kind of things you can do with all these newfound pieces of information that are coming your way. Yeah. Yes. John?
I think this was I said earlier today a few times by myself, Ronaldo, maybe others, but the scheduling, the combination of that with the physical layer and position dependency along with time dependency is an opportunity to make significant improvement when the network is congested. And then we get into whether it's congested or not if we get more spectrum. We talked about it, but smarter can help in that situation, better prioritize or allocate space, time, frequency, or energy to each of the users.
I just want to give another short example how it can help. Is one of the problems that we had with 5G is in the millimeter band is tracking, beam tracking. Very too slow for to track where the traffic is. So the sensing, etc., it is like a camera. Put it this way, like a camera, you know the person is moving or the vehicle is moving, so you move before it actually gets to the next point. So that substantially helps the search algorithm to minimize the delay as well as the accuracy of the beam steering and tracking and maintenance for it. I'll give you an example. There's so many examples you can give. All of these are subject to a huge amount of research to be done.
Tracking is a good one. I just wanted to emphasize a little more on the semantic aspect. And let me give you just exaggeration sometimes is the best way of explanation. So suppose you are trying to send a massive book, War and Peace, right? Well, I should only need to send the ISBN number, and the other end knows how to pull that out of a library. Why do I need to send the entire, how many pages it may be? I don't care about the font, I care about the content, right? But how do we make use of this higher level knowledge to push it all the way down into the app? That's where the challenges is. And that's, of course, is an extreme example. But in between, there are many, many others. You're taking a picture of a scene. Do you want, what we are doing today in this other media, except for voice, or let me wind up the clock a little bit. We started with tone quality voice. John would remember when we were colleagues at AT&T, tone quality and mean opinion scores were the king. And if it was not 4.5 and higher, it was not deemed appropriate for telecom network. We moved from that into mobility, with mobility being so valuable that we were willing to sacrifice quality. So we learned how to compromise on quality all the way down to 9.6 kilobit per second variable rate voice encoders, with the quality that sometimes is really pretty appalling. For everything else, we are trying to keep high percent fidelity, super high audio resolution, super high image resolution. While that's exceedingly interesting work, you take a photo and you can detect this area is grass, this area is mountain, this area is sky, and now AI at the receiver can regenerate your photo. And with different degrees of fidelity. Is that blade of grass exactly the same? Well, it's second order the same, but don't ask for every instantiation of every blade, and so on and so forth. So I think this space is just wide open. The performance enhancements are amazing, but I think the pitfalls are also quite challenging, because where do you draw the line that you lost too much fidelity in to achieve the performance gain?
So I know it's very good, because when we discuss then new ideas, new things that comes up, as traditionally we've always been obsessed with the quality of service, bit error rate, SINR, and frame error rate, and et cetera, et cetera. With the new neural networks, with AI and et cetera, perhaps we should switch to more, rather than quality of service, to quality of experience. Then we are not dealing with such a strict parameters and KPIs that traditionally we've been working on. If the quality is good enough and the SINR, for example, is very low, I'm happy. Why should I have a certain SNR at 10 dB or 7 dB or whatever it is to give me the quality I expect? Perhaps we should switch with 6G and future systems. We should probably put more and semantic communication with the AI and etc. We should probably design the system with the quality of experience in mind rather than quality of service.
So I think for this keyword smarter, so I think there is no free lunch if we want to make it smarter. So we have to get or dig some the additional information or think about some the multiple domain knowledge to make it smarter. If we go back to the pure signal processing, yeah, that is the pure theory, and then all the knowledge there, so we cannot do smarter. However, if we go to the context of wireless, so as you said, okay, so how about the end-to-end, the QoE or QoS, the metric, or for example, we consider the multiple domain signal processing methods. For example, not just the pure signal, the visual, or we can have such as the other signal processing method. We use not only for the radio, probably we have the video, the beam, the laser beam to help us the locate the user, and then we can search or help that detection in that region that make the more efficient. Or for example, if we consider the beam tracking, you mentioned that especially for the low altitude economy or the drones. So how we can at the same time sense the drone and also communicate. So not if we just rely on one dimension, just the signal, the radio frequency propagation, that is quite limited. If we also use the visual image or video to capture, okay, the rough direction of this the user, the UAV user, so we can beam the signal in that direction on standard radar wave. So then that helps us to make the signal processing smarter and quicker. So also another possibility that we can utilize multiple base station to make the collaborative the signal processing. So there are more information we dig and then we utilize, then that could be smarter, I think. Yeah.
Yeah, I agree, and just going back to the quality of experience, the reason why we focused on the more traditional metrics like PSNR and so on and so forth is because they were correlated to the quality of experience. You didn't send me the frames, or you send me some over compressed images, my quality of experience will go down. But nowadays you can synthetically generate, right? So I can get a frame or a video sequence that is not up to par, and then I pass it through some kind of diffusion network, and then generate something that looks amazingly good. It may not be the same, but if I don't care if the tree is this way or the other way, at the end of the day, I have the same visual sensation, right? So is this synergy of tools that are coming from the computational community, right, and the things that we are doing, that I believe they give us a lot of space to work, right, and come up with new ideas and suggestions.
So I have some additional question. So do you think, in this sense, that neural network will be like JPEG? Version by version by version, we have a standardization, or it is self-generated. When you turn on the network, there will be data. It come out individually itself, and then there is this interoperability problem. What to do? So are we finished the compression standards become truly data-driven, and then there is two versions of a neural network, how they learn in each other. This is the big if it is interoperable, that will be very nice. Then we finish a lot of complex process on this part. Otherwise, it will be yet another very difficult, painful process to go through.
One thought I have on this, and it's a little bit tongue-in-cheek though, but it is, I mean, especially that section of the 3GPP standards on the voice compression, it's almost impossible to read. There are mistakes, and then if you weren't there when they wrote the standards, you're not gonna even ChatGPT can't figure it out. I had occasion to try to look at this and figure it out. Would we be better off if we were sending robots to the standards meetings to actually write these documents in a way that we can understand them better than because if you weren't there, it's almost impossible to back engineer from that standards document something that would interoperate with another product. And in a way, it's kind of unfair. As you read through, you can guess that this must have been one company's patent, this must have been somebody else, some other company's patent, and there's stuff in there that maybe doesn't need to be in there because of, so that whole process could probably get a lot better so that it's more accessible. And would AI help that by reducing the need for standardization, or does it increase the ambiguities that the two sides that are, do they have to use the same AI algorithm, so forth, to produce is interesting. But, AI is replacing a lot of other jobs, maybe standards, or for that matter, lawyers, doctors, and other, and maybe engineers as well. But it's certainly, it would be nice to improve so that someone with a reasonable background in engineering could take one of these standards documents and, with some work, be able to understand it and develop from it.
So, if I may follow up on the standards. So first, let's recognize that standards has enabled this amazing, over the last 20 years, $1 trillion business, and very useful. I mean, they say that it's not even a joke that babies almost come to the world already with a cell phone in their hands. And so why? Because it's expected, useful, everywhere, anywhere, at all times. So whether you are handing over from one base station from one vendor to a base station from another vendor, whether you are in one country or another country, you get off your plane, sometimes in the plane, and you have, it works, it just works. So the user doesn't even know that you change all of these variables under the system. So has proven to be interoperability. Global interoperability has proven to be incredibly valuable. Having said that, and particularly in the monostatic sensing, when transmit receive are in the same location, perhaps of the single vendor base station, why do I need interoperability? I need to operate with multiple handsets, that's true. But if I'm doing passive target detection, would not involve me by the handset, do I even need to standardize what I'm doing? Perhaps there is opportunity for new applications that are outside of the standards, where a vendor of a particular base station can, leverage their hardware and software on a side-by-side basis for passive sensing. No need for interoperability there. So there may be a lot of new applications where the standards are not solution necessarily for everything.
Yeah. For monostatic sensing, yes, but that's only you have only 20% of a view of the real environment. So there are a lot of none of a side and other type of limitation. But then if mobile come to into play, you get more more views and physical data that enable you to reconstruct everything, if it is that is the case. So the one that I'm leading to, if we do not have a standardization, then we need to have some common training, distributed training mechanics, so that the data-driven, that actually the standard version is a live one. It is keep evolve. Otherwise, we have to sit there at agreement and then go back to implement. So this distributed training mechanics, that if it is the neural signal processing will be there, that will potentially a key mechanics to be there. Otherwise, it will be not as scalability as you said, because if some base station may train, some may not train, so you don't get any benefit, and then you are lowered down to the minimum performance.
I think this is a good point that you mentioned when, first of all, we know that not everything gets standardized. I mean, we just, for interoperability's sake, that items are different areas standardized, otherwise the rest is not the standard. So perhaps what I'm going to say is more like a question probably and a comment, a mix of those. Perhaps quality of service, the way we've been defining, is easier to develop interoperability and KPIs that we have, because it's based on quality of service. When it comes to quality of experience, it opens up. It's difficult to standardize. Is that what you? That's why you asked the question. Is that?
Yeah. So more or less on the soft metrics.
It's on the eye of the beholder. So it's not as cut and dry or very objective, if you like, as the quality of. Yes, that's right.
Yeah. So the diverse of this type of thing is not easy, as Renato was saying, that the more score will categorize. Okay, this is a good quality, and that quality. Maybe there's no objective or subjective mapping.
Well, I do believe, that, as I always say, the proof is in the pudding. So you have to try, and I'm pretty sure that they will try, or someone will try, and then comparisons and will be made, and conclusions may be drawn. Now, if it is on the form of a standard or a standard process, or it can be on an ad hoc basis, that I don't know, but I'm pretty sure that activity will take place.
just again, off the hoof sort of comments is perhaps in order to be able to engineer qualitative experience we need user feedback. You know, to say that the quality is bad and then the network will enhance the quality or vice versa. But
that's the power of a mobile network. Yeah. You have billions of feedback.
I think the world of users is split in two camps. Those who answer every survey and those who don't. So your sample is going to be biased.
Usually, those that they reply, they are not very happy. They are not a happy campers. But this opens, obviously the question of, the real time, right? And you need to collect this information and the feedback, on the time scale that allow you to do the changes. It may be tools as well, like reinforcement learning with, human feedback that have been tried in other contexts that can provide, some venues or avenues, I should say, right? Down the.
Yeah. Can I just add one quick one? On our phone, when the sound, the volume is low, we just increase it. Yeah, that's what we do. It's a button. If the quality is bad, why don't we have a button to say we need better, better, and better? Real-time feedback providing and improve. We always start from the worst case and then we improve it over the time. Why not? Why can't we do that? That's my question.
So it looks like one size model fits all is not there, so that the reinforced learning will be the mechanics that actually can solve several of this problem in the question.
Yes, and although the reinforcement learning and its varieties are not part of what we envision as reasoning enhanced neural network, I'll try to jump to the second question. Then we can discuss that as part of this. So the idea for the question number 2 that you see over there is that there is an agreement that traditional neural networks, they don't do the job for the very reasons that we discussed today. So the question is, what else we can do? So the idea is, can we, for example, combine the data-driven solutions with some classical knowledge style learning? Can we use model-based neural networks? Can we use physics enhanced or driven solutions to get better results? And if this makes sense in the kind of environment that we're considering right now, being the communication systems, the 6G, and so on and so forth. And lastly, how we go from learning something to really understand what's happening and translate this understanding to action, right? So, we have an actuator that does something and changes the way, the system operates.
Yeah, so a quick comment on the quality of experience coming from a propagation guy. So if you are right under the cell versus at the cell edge, and I'm not talking about 100% because in propagation, in coverage, and coverage is king in cellular, that's never 100%. So you achieve a 95% coverage and you've already exhausted what you're willing to invest in terms of resources for the edge users. Now, if you happen to be an unlucky edge user and you're disadvantaged by 70 dB over somebody who is right at the core of the cell, it doesn't matter if you have a button to press or its intelligence is detecting that you're not happy with performance. The service provider is not going to all of a sudden stop the traffic of 99% other users just to devote the entire cell resources to improve your link. It's already doing best possible scenario, scheduling, rate control, modulation encoding to achieve a very carefully crafted balance between investment that it was done up front in in resources and quality of edge performance. That is, you can see pages and pages of TDocs in 3GPP where they carefully craft to achieve this trade-off. So I am a little hesitant on how much gain you're going to get from real-time trying to re-optimize this trade-off. Of course, the 3GPP trade-off that I talk about are static and given on specific scenarios. You may be able to do something in time of day. If you are the only user middle of the night, sure, why not? Put all the power onto that one edge user. But it's going to be corner cases, not the peak hour maximum traffic where that's where the money counts.
Oh, sorry.
Okay. So what I was going to say is there may be an opportunity for these adjustments, whether real-time or near real-time, more where there's changes in the mix of services, not the QoE of a particular one, but the QoE of the subclasses, because as the mixes change, the manner in which you service them may differ.
No, I just wanted to respond. When you allocate resources based on the experience that you have. If you are center of the cell, probably you get one subcarrier and high-level modulation scheme. It meets your requirements. Then you, at the cell edge, you got BPSK and you get a bigger bandwidth, for example, etc. And then you meet. So if you provide resources based on the quality of experience. To be honest, I'm not too adamant about this quality of experience because I need to learn about what we can use that one to manage the network. But I'm just saying that if you allocate sufficient resources to meet the quality of experience, perhaps you have more resources left for the cell edge users. Could be. But we don't know.
Yeah, perhaps, but when you hit the bottleneck of the coverage or bottleneck of the capacity, I have some doubt that neural network can produce some magic. That's what probably we are on the same page on that.
Physics is the law.
Yeah, so for this problem, I think about the one example that you mentioned that pilot. We usually use pilot for the channel estimation, and based on the result, we make the signal detection. And then also we know that for the dynamic broadband channel, so if we embed more pilots in different time frequency slots, so we could get better results of the channel estimation. But on the other hand, we had less resource for the data transformation, so we lower the transmission efficiency. Then recently, also our group focusing on this problem, how we could use the neural network to help pilot, the least number of them pilot, to make the balance, to maximize the benefit of the neural network. So if we use zero pilot, then we cannot learn anything about it from this channel. So we use minimum number of pilot to learn some of the basic property of the channel, some the relationship between the channel and its time varying effect, and then we use the neural network to develop more or synthesize more data of the channel, and then for that, so we can get the better results for the channel estimation and detection. So that is the example we can use the neural network to help us. So that's the balance. Yeah. Another factor is that if we consider the drone UAV communication, we add another module to mimic, to simulate the flying track behavior of this UAV, because we know this flying path, we know this speed cannot suddenly change. We know the model of the flying, and then we also can embed it into the neural network.
Which actually, brings me to the question number 2 on the reasoning enhanced neural networks, where basically you're using physics or information that comes from the knowledge and understanding that you have about the problem, right? To guide your network rather than solely depend on training, right? It's just the classical sense. You put the training data, you put the labels, and hope for the best. Here you have the laws of physics, right? That they dictate certain courses of action. So do you think that there is? I mean, there is this kind of activity in general, but the question is something like this more beneficial or more appropriate in the setup that we discussed right now? You have, a 6G network, or you have a communication system, right, that has to obey, certain rules of nature. So the question is, how we can go about in infusing knowledge and handcrafted, knowledge and ideas that we have into the network, and how we train and combine the two of them. Yes.
So I guess you're moving to number 2, right?
Yes.
So at least in my understanding, I think when we talk about this reasoning enhanced neural network, I think we're trying to combine or integrate structural logical reasoning, basically with neural networks, with the hope that we can enable system to perform complex tasks, and basically by doing inference as well as contextual or circumstantial understanding, right? And I can see that there is a lot of potential in this context. So maybe I can think of 2 examples. I think all of us are familiar with data-oriented communications, where basically based on Shannon theory, where basically the most important item is reliability, make sure that the bit rates is, the bit error probability and so on. That's what we're trying to emphasize. But now we're talking about AI, machine learning, and so on. And sometimes what is really important is basically trying to achieve something, right? And this leads to something different. Instead of talking about data-oriented communication, we talk about task-oriented communication. So, for example, let's say I'm trying to understand, trying to look at an image, I'm trying to understand, is this a dog or a car? I don't care basically whether the error probability is 10 to the minus 9 or not. I want to make sure that I can say it is a cat or a dog. So this is what I refer to as task-oriented communication. And in this context, this reasoning enhanced neural network can help me, for example, to dynamically optimize the resource allocation based on inferred, basically, goals or tasks. So that's one example where I can see this is important. Another one I mentioned this morning also, I think some of us mentioned semantic communication, right? So in this context, by combining pattern recognition with symbolic reasoning. So I think we can improve the efficiency of semantic communication. For example, we can compress the messages while preserving the meaning. So in a way, I can see that I'm doing neural network and reasoning at the same time. So these are 2 examples where I can see this idea of reasoning enhanced neural network can be very useful.
I was just trying to bridging how the large language model to the reasoning stuff. So it is like in our communication language, is like if you do every bit with hard decision, so you get very high bit error rate. This is what Renato was talking about. Ask one question, they will give you probably a lousy answer. But what the neural network, the large language model to do reasoning these days is that they don't give you immediate answer. They will ask themselves many, many questions. So they will put several hypotheses like a Viterbi decoding. So they will keep all this without showing you, and then they will use knowledge to check which path is the valid one. So it's the CRC that we use. And eventually, they, instead of the detection a single bit with a very high risk, they detect a sequence. So then they come up with a step-by-step reasoning more become, the reasoning style to produce a reliable answer. So this is one methodology that they progress, not by chat box, immediately answer by and then reply, because this is like a random drawing almost. But then you produce large sampling, and as well because it's built in the so-called chain of thoughts. So there are some knowledge or some logic behind, then you validate. That potentially could be applied for many of these the scenario that the panel talked.
So a little bit of a controversial comment, but see if you agree with me. It sounds to me that the AI community loves to use this grandiose language. But to me, the one-shot detection is the classical inference.
Yes.
Well,
it's an inference.
Adaptive
it's not reasoning.
Yeah, adaptive coefficients is you just steep descent, approximation. You tune the coefficients. So that's the training part. The inference is the one-shot.
One shot, yes.
Which is the maximum likelihood single token autocomplete. And then the next one, which they call reasoning, and I beg to suggest to the panel that this is a really pompous overstating of the name, is simply maximum likelihood sequence estimation.
Yes.
So instead of giving you one shot, they evaluate the probabilities of multiple sequences, they keep them alive, and they present one to you. We used to call this maximum likelihood sequence estimation, and nobody in comp theory would suggest that this comes anywhere close to reasoning by humans, or let alone understanding. I think among psychologists, there is a heated debate. What does understanding really mean? So if we don't know what it means, how can we say, we achieve it with the neural network, with machine learning, or whatever you want to call it? Just my personal bias on keeping the language a little bit under control with the hype.
Yeah, so it's not yet hyped yet, but this is the step that start to dealing with the math problem, because you have a step 1, step 2, step 3. You cannot miss any step. So this is end coding as well, but not as not a humanity understanding, but the bounds, the one that some knowledge, some per hour rule on top of that, it's like almost like communication CRC check. So that's right.
Yes, so this, slow reasoners, that they take a bit more time, to reason or perform maximum likelihood detection, whatever, is one thing. How about, this idea of causality, which is usually overlooked in typical, computer science applications, right? They don't really differentiate between correlation, right, and causality. Do you think that there is a room there for things that they should be done differently?
Well, you just touched the raw nerve for me, because this is a very, very nice example of how the two camps, call it human psychology versus machine learning group. Machine learning group, of course, does correlation and has no clue about causality. The set of adapted coefficients, no matter how large your training set, or whether you do it one shot, autocomplete with single tokens, or whether you do it keeping sequences alive, absolutely no sense of causality. Causality is already a very complex concept. What about common sense? Is another big question waiting to be asked is, do the neural networks have common sense?
They do not have that foundation. That means, say, if on the Earth they can have all the human language, there may be only one human or two human foolish saying the apple will fly, but then they can conclude all the phenomena they observe. They maybe eventually reach the conclusion it will fall down. But if you have zero data in Mars, they cannot, as a Newton or powerful, saying that, oh yeah, but it's universal, because they have zero data. That's where all the data-driven mechanics as.
That's a beautiful example that connects with the topic we were discussing in the morning about fundamentals. So the machine learning, if you say, will the apple fall in Mars? Boom, complete disaster, has no data, it didn't train on Mars data. The scientists will say, well, let's see, what is the mass of Mars, what is the mass on Earth? It will fall, and it will fall at this rate, give to the gravity of that planet. So, I mean, this is how huge the gap, cognitive gap, can be at times. So I think we really need to sometimes slow down the hype a little bit. Good example.
Yeah. No, wait. I'm gonna talk about that example. Is AI ultimate goal is to think like human being. That's ultimate goal. And if I don't know anything about Mars, I don't know anything about it, I'm a human being. If you say, the apple will fly or will drop, I will say, I don't know. So what's wrong with AI to say, I don't know? What's wrong with that? AI is not the magic to say everything, have answers for everything. I think we have to be a little bit realistic.
But following your point, which is a very valid one, I don't want to be refractory to everything, but if humans take a good 5-6 years to start to move in the world, 3D world, and start making sense of objects and animals, and then it take another 7-8 years to read and write and start getting the basics of arithmetic, and then a full high school before it have a little bit of history, biology, chemistry, and then college education. So we're talking about 12 years of formal training in school, plus 5 years of training at home, plus a lot of physical interacting with real world. Talk about physical AI ML. Are we willing to wait for 18 years for a piece of software to become human-like?
Machine works much faster than human being. So
I beg to differ. I think,
okay.
Here
and they can learn. For example, which human being has learned 95% of the data on internet in their lifetime? Machine did.
In certain corner cases, you're absolutely correct. And if you train it with the entire database of internet, of course, no human can actually possibly imagine to consume that amount of data. But it's not an intelligent consuming. It's not understanding. It's correlation of tokens. So, for instance, this is another example. A little baby sees one cat, and from that point on, it knows what a cat is, or he or she knows what a cat is. You don't need to present the baby with different species of cats. How the brain does that is, big mystery. But you show one cat, one dog, and that's enough for a human being to know the difference between a cat and a dog. Any machine learning is completely lost, right? With an example data set of one entity, it's hopeless.
You
wanted disagreement in the morning. Now I think we are getting disagreement here. I think we need to say what we expect from AI to do. I think we need to set our expectation, because our benchmark, again, I can mention benchmark, is average human intelligence. That's what we are trying to say. We said common sense. Average human person is got a common sense, all right? And that is the way that AI is going to do with AGI and with everything else. I think what is probably missing is, in my opinion, is AIs to understand emotion. For example, to understand I'm happy, or I'm angry, or I'm under stress, and sort of thing. You can, because we work on semantic communication, you do a bird, and then you give another picture of the, you train it on the bird, and then you give a rabbit, and then it produces rabbit. It doesn't need to be trained again and again and again. And if you put my face to semantic, it may turn out to be, I look very angry, but well, I'm not, I'm happy, for example. They doesn't understand the human emotion. For us, bird looks the same, doesn't look angry or doesn't look happy or whatever it is, so it is easier to generate that. So I think the emotion and common sense needs to be added somehow to the AI to be able to say is comparable to something that average human being intelligence is.
So let me take it a little sideways. I think we're departing a little bit of the agenda, but if the chairman wants to bring us back on topic, be my guest. But if not, an area of agreement perhaps is we move away to trying to imitate humans of when could we have AGI, which is highly controversial. But an area that AI, I think, could become immensely valuable is when you combine it with the robotics and with the physical. So cyber-physical integration. So, however, the challenges, they're not insurmountable, but they're still very, very large. So if you put a teenager in a kitchen and ask them, make me breakfast, it could be complete new house of a friend's house. Teenager will know which drawers to pull to try and find the utensils. Teenager will know that he has to go to the stove and how to operate the knobs. Doesn't need to know the model and the manual and instruction set. Doesn't need to see a gazillion versions of different stoves, et cetera, et cetera. Human, it's accumulated knowledge base, if you want to call it, or adaptive to environment. Context-specific knowledge base of the human. How is it acquired over many, many interactions? How does inference from my kitchen to completely unknown kitchen? It's not by being fed all possible kitchens on the universe. It's extrapolation. I know my kitchen, and then I can guess from other people's kitchen. So this is a huge challenge in robotics today. You can have a robotic welding doors into a car, fantastic, better than any human operator, but it cannot make breakfast.
I think Ben has got
so
access to
this
that.
is the precise value for sensing.
Yes,
because
exactly.
human knows the workflow of the kitchen, but in that precise room, if without sensing.
Yeah, just from an anecdote from my days when I was young, I have visited Hans Moravec. At that time, I still believe he's still in Carnegie Mellon in Pittsburgh. He's the famous guy with the Mind Children, his famous book, and the Moravec's paradox that says, well, the robots, because he was a robotic theorist, right? The robots can do all kinds of difficult things, very effectively, but they fail, the task of 1-year-old, kid. So yes, we have come long ago from those days in the 80s, but still I think we have plenty of space to cover. But it doesn't mean that we cannot do other things. So I am on the same camp with Tonga, because the more you acquire information, right, from the sensing and the environment, etc., the better you be. Positioning yourself, right? To do the things that you really need to do.
And maybe in the meantime, we're still going to be relying on huge data set. This is where I liked your comment on the networked. So if I still need to see a large variety of kitchens to learn how to do things, maybe the fact that through the network I can have a pick. Of course, privacy issues need to be addressed, but the network has seen many, many kitchens, and maybe this information can be collapsed into one particular instantiation to achieve a particular goal.
So the RF sensing is more privacy preserving than the RGB.
Indeed.
You'll make a lot of friends in the JPEG standardization committee. So my boss here, told me that I have to move on the question number 3, which is techniques and challenges, and you see some of the we have discussed through the day some of these challenges. We don't necessarily have to repeat all of this. So any new suggestions, recommendations, pearls of wisdom, if you like, on how we can go about addressing some of the challenges and move the needle forward towards something that is much more useful at a reasonable cost.
too early to say these networks, which one will pan out eventually.
So Khalid, I'll put you again on the spot. You you told us about the graph neural networks, right? And non-linear connection on data. You think that is it something that we can use to our advantage?
And I mean, at least the way we actually, what we did, we started looking into traditional neural networks, and a lot of people have done that. And I think what we have found is that it is very difficult to generalize the use of traditional neural network to do optimization, resource allocation, or traditional things that we do in wireless communication. So the next thing we did, we used something called imitation learning, which is kind of a combination of reinforcement learning, and we found that it's actually way better than traditional neural networks, but still, it takes a lot of time, and then it's not really truly scalable. So when we finally we've looked at the graph neural network, and we find it really to be extremely good. So in my view, it's something that is really worthwhile to look into, and I think the most important thing is this idea of scalability and generalization, and also it's relatively fast in terms of computational complexity. So the answer is yes.
Thank you. Anyone willing to take a shot on the other names that were dropping on the slide? Temporal reasoning, probabilistic reasoning, and the rest. We already touched upon reinforcement learning. Yes, it does have certain appealing features compared to other supervised type of learning, but they have their own problems as well, right? Some of the assumptions, for example, that the Markovian nature, that you completely understand, and how the chain unfolds, all of these things, they are far removed from reality. The integration with real-time systems, to me, it's the real sticking point, right? So how you can make, I may be wrong, but my thinking is that this is probably the most important thing, because it opens the door potentially to have big problems, right? You can have catastrophic errors. You can bring the whole system down. So any thoughts, any opinions on the matter?
No, that's what I said this morning. I said in the protocol stack, if you go from application layer all the way to the physical layer, that non-real-time aspect of the becomes more pronounced and becomes problematic with the state-of-art research that we've done on the AI neural network. So it becomes critical and requires further research, because time critical or time, the time scale for the physical layer is microseconds and millisecond maximum. Can we do, even with small agents, and so can we achieve that real-time aspects? I don't know.
With the current the neural network structure or method, 500 billion coefficient is a dog level of intelligence. So that time scale you go up to a half second of one inferencing. So for the real time wise, unless you reduce the so-called intelligence level, very, very specific task, you can maybe close to real time. But if you have a very general intelligence, dog level, let's say, or I think 100 billion is the rat level of the intelligence. So that those are depends on where we go. But in the end, the big intelligence in the data center, So that's no doubt about it. So there is a network is a step you never can skip if you want to have a human or superhuman level of intelligence, because there is no way Moore's law, although it's stopped, can shrink the brain into the phone. So that's not possible. So that networking will be there. But in terms of real time or non-real time, for network itself to apply AI, I think that's implement the engineering or physics. There's a limitation.
So I would imagine I would get no argument, and so this is counter the excitement of controversy, but to touch on things that give us hope and inspiration for immediate future work. If we start at the highest of the pyramid with resource allocation, network management, operation management and control, it's clear to me there are tremendous gain to be had. There's knowledge-specific, the application-specific knowledge that can tremendously aid on the specificity of the task at hand, the agents, etc. And the level of intelligence, now that you've defined a very specific domain, becomes manageable, and the timescales are also generous. As time progresses, we can expect make inroads to the next layer of latency, short-term latency, and more ambitious intelligence. But at least I think there's tremendous gain to be had, as John was saying before, even at the resource allocation and network optimization, management, operations, and control.
So in other words, the low-hanging fruit is on the top. So from a pragmatic point of view, this should be the starting point, and then progressively, you will see how you move the needle, right, and you get further advantages as you go down the pyramid. Okay. Any other comments? Yes.
I would just say that, I don't know, I haven't come across one single technique that would probably meet most of the requirements of the system, different aspects. Possibly it would be a combination of the different techniques, and it's horses for courses, as they say. It's not one solution for everything. It's going to be, depends on the problem.
Well, but I just want to respond to what Renato was talking about the kids. I guess still the pre-trained model has some merit. The GPT is the pre-trained transformer, because the kids is inherent a lot of genes, pre-wired intelligence already. So these some 4 years in the infant stage or children's stage, and the recognition the cat, it probably just the trigger to excite the machine. That's probably, but probably it's already pre-wired in the biological system.
Well, it's very possible that we inherit the instinctive capability of differentiate between a cat and a tiger.
Obviously, because those that they didn't make it.
The genes didn't make it into the pool.
That's right. It's called natural selection.
Thanks, Costas, for hosting the panel 4. There's a lot of interesting debates, and also the participation for the discussion is wonderful. I would like to extend my sincere thanks to everyone who is here today to participate this salon and to make wonderful contributions. So thank you, and we adjourn the salon, and then we come back to this room at 9 a.m. tomorrow. Thank you.
Thanks, Chairman, for organizing this wonderful salon. Thanks.